Everyone is excited about Monad because of its speed. We're talking 10,000 transactions per second at launch, which is absolutely crazy compared to even a really fast network like Solana, which operates at about 1,000 transactions per second. Furthermore, it wants to optimize the Ethereum virtual machine, or the EVM, which is going to allow our developers who know Ethereum to be able to do the exact same thing they're doing today, but on a much faster network. The big question we want to ask is how? How is Monad able to accomplish these incredible speeds even compared to other modern networks? Well, this comes down to the four key components of the Monad architecture, and we're going to go through each one of these at a high level. Let's start with optimistic parallel execution. Wow, that is a mouthful. What is it saying? Well, what it's saying is that in traditional blockchain, we have to look at our transactions in serial fashion, meaning that if I have 100 transactions, that I have to look at them in order, which we might say makes sense because this transaction might depend on this transaction over here. Maybe this one completely wipes out an account and this one tries to use the funds in that account and it gets denied. But what about these transactions which have nothing to do with those other ones? Why couldn't they be run up here? That's exactly what parallel execution does. In Monad, we're able to sort out the transactions that are dependent and run those serially while running other transactions independently of that. And so we can calculate out the result of our transactions much, much faster. Next up is asynchronous execution, and this has to do with the concept of slot times. With our other modern architectures, we're going to have hard set slot times, more or less, that require us to abide by, let's say, 400 milliseconds that Solana and Monad both have. And so what happens here is that a validator is motivated to consume this entire slot time to try to find the most valuable transactions that are out there. And so we're going to consume all 400 milliseconds because even if we get done early, let's say we get done halfway through, we can't do anything with that until the next slot time begins. So why not chew up all of the slot time? Well, with asynchronous execution, with Monad, that means that we are in async mode, meaning we're out of sync with one another. And that's actually a very good thing here. What Monad does is, again, we're still using 400 millisecond slot times, but if we do happen to get done with our forming or creating a block halfway through that slot, then we can actually start processing it immediately. We don't have to wait for the next slot time to do so. And so this makes us even faster, which is why Monad says that we can achieve consensus in 2 slot times, which is 800 milliseconds. Absolutely incredible, especially compared to Solana, which is considered fast at 12.8 seconds. But by comparison, that's an eternity compared to 800 milliseconds. Now, next up, we have a couple of Monad-specific architectural components that are worth paying attention to, because they also contribute towards speeding up the network. The first is this concept of BFT, which stands for Byzantine Fault Tolerance. It's a well-established method for achieving consensus, and it's used by most other blockchains. Now, Monad BFT takes a very optimized approach. We are going to base this on a method that is going to achieve consensus much faster. Now we're talking at a very high level here, so we're not going to go into the details of this in this video, but we will talk about this in a future video coming up as to how exactly we achieve faster times. The point is that while all these other networks are all using some form of established BFT, Monad went out and created an original format for how to achieve consensus, and it's one that is highly optimized compared to what all these other networks are using. Lastly, we have the database, or MonadDB. The underlying database is a custom state database, which sounds really fancy, and it is, but ultimately this is going to lead to further optimization. We maybe are noticing a trend here. We see that this is optimization at the database. We've optimized BFT. We have optimistic parallel execution. We are optimizing things everywhere we can to help achieve these speeds. MonadDB was built from the ground up for Monad. And while most of our networks deploy their databases into RAM to make it as fast as possible, That's not required with MonadDB. In fact, it can run straight from the SSDs, which drives down the cost of our node requirements. And if it doesn't cost much money to deploy a node, we know that this is going to help with the mission of decentralization. Monad expects to become more and more decentralized over time rather than what some of the other networks have experienced, which is that they become more and more centralized over time. And we know in the blockchain world that decentralization leads to network security and strength. So we might look at Monad's speed claims of 10,000 transactions per second and question how exactly they are doing this. But we find that these 4 different components to the Monad architecture are what really bring it together and make it all succeed. So like this video, subscribe to the channel, and always remember to stake at the lake.